Hey everyone, and welcome back to the channel. Today, we're diving deep into something we all interact with daily, our food. Specifically, we're going to uncover the fascinating, and sometimes surprising, chemistry of animal products and what it means for our safety. From that juicy steak to your morning eggs, there's a world of science happening on your plate. Let's start with meat. When you cook a piece of meat, you're not just heating it up. You're initiating a series of complex chemical reactions. The most famous one, the Maillard reaction. This is the magic that happens when amino acids from proteins and reducing sugars react under heat, creating that beautiful brown crust and a symphony of savory, roasted flavors. It's not burning. It's a controlled chemical cascade that makes food delicious. Think about the difference between a boiled piece of chicken and a pan-seared one. That difference is largely the Maillard reaction at work. But heat does more than just create flavor. It's also our first line of defense in food safety. Raw meat can host a variety of microorganisms, some of which can be harmful, like Salmonella or E. coli. Cooking to the correct internal temperature is crucial because it denatures the proteins within these bacteria, essentially scrambling their internal machinery and rendering them harmless. That's why a food thermometer isn't just a gadget for pro chefs. It's a vital tool for every home cook to ensure their meat is both delicious and safe to eat. Now, what about the color of meat? Why is fresh beef bright red, but sometimes turns brown? This is all about a protein called myoglobin. In the presence of oxygen, myoglobin forms oxygen myoglobin, which gives meat that cherry red color we associate with freshness. Over time, or with less oxygen, myoglobin can oxidize into metmyoglobin, which is brownish. This doesn't necessarily mean the meat is spoiled, but it's an indicator of how long it's been exposed to air. Cured meats, like ham or bacon, get their pinkish red color from a different process involving nitrites, which react with myoglobin to form a stable pigment that also helps prevent bacterial growth. Let's move on to another kitchen staple. Eggs. An egg is a self-contained marvel of chemistry. The yolk is rich in fats, vitamins, and a fantastic emulsifier called lecithin. Lecithin is what allows oil and water, two things that normally don't mix, to come together. This is the secret behind creamy mayonnaise and smooth hollandaise sauce. The egg white, on the other hand, is about 90% water and 10% proteins. Like albumin, when you whip egg whites, you're physically denaturing these proteins, forcing them to unfold and trap air bubbles. This creates the stable, airy structure of a meringue or a soufflé. Adding a little acid, like cream of tartar or lemon juice, can help stabilize this foam even further. From a safety perspective, eggs, much like meat, can be a source of salmonella. This is why we're often advised to cook eggs thoroughly. The heat denatures the proteins in both the yolk and the white, turning them from liquid to solid, and neutralizes any potential pathogens. Pasteurized eggs, which have been gently heated to kill bacteria without cooking them, are a great option for recipes that call for raw or lightly cooked eggs, like Caesar dressing or homemade ice cream. Next up, let's talk about dairy, specifically milk. Milk is an emulsion of fat globules suspended in a water-based solution containing proteins, lactose milk, sugar, and minerals. The two main proteins in milk are casein and whey. When you make cheese, you're essentially manipulating these proteins. An enzyme, often rennet, is added to curdle the milk, causing the casein proteins to clump together and form solid curds, separating from the liquid whey. The variety of cheeses we have is a testament to the different ways this process can be managed, along with aging and the introduction of specific cultures. The safety of milk is largely managed through pasteurization. This process, named after Louis Pasteur, involves heating milk to a specific temperature for a set amount of time to kill harmful bacteria without significantly altering its nutritional value or taste. Before pasteurization became widespread, milk was a common vehicle for diseases. Today, it's one of the safest food products we consume, thanks to this simple yet brilliant application of food chemistry. But what about lactose intolerance? This happens when a person's body doesn't produce enough of the enzyme lactase, which is needed to break down lactose, the sugar in milk. Undigested lactose can cause discomfort. This isn't an allergy. It's a chemical incompatibility. Lactose-free milk is made by adding lactase directly to the milk, which predigests the lactose into simpler sugars, making it easier for everyone to enjoy. Finally, let's touch on seafood. The fishy smell we sometimes associate with older fish is caused by the breakdown of a compound called trimethylamine oxide, or TMAO, into trimethylamine TMA. Fresh fish has very little TMA, so a strong fishy odor is a good indicator that it's past its prime. A squeeze of lemon juice can help. The citric acid in the lemon reacts with the TMA, converting it into a salt that doesn't have an odor, effectively neutralizing the smell. It's a simple kitchen chemistry trick. Seafood safety also involves being mindful of cooking temperatures to eliminate parasites or bacteria. But there's another layer: heavy metals and microplastics. These are environmental contaminants that can accumulate in the food chain, often concentrating in larger, predatory fish. This is a complex issue where food science meets environmental science. Health authorities often provide guidance on which types of fish to eat and how frequently, especially for vulnerable groups, to help us make informed and safe choices. So, as you can see, the journey of animal products from the farm to our fork is a continuous story of chemical reactions. Understanding this chemistry not only helps us become better cooks, creating more flavorful and texturally pleasing dishes, but it also empowers us to handle our food more safely. It turns our kitchen into a laboratory of delicious discovery. From the sizzle of a steak to the whisking of an egg, chemistry is the invisible chef that helps make our meals both delightful and safe. Thank you so much for joining me on this deep dive into food chemistry. I hope you found it as fascinating as I do. If you enjoyed this video and learned something new, please give it a thumbs up. And don't forget to subscribe and hit that notification bell so you won't miss our next culinary science adventure. See you in the next one. Hey everyone, and welcome back to the channel. Today, we're diving deep into something we all interact with daily, our food. Specifically, we're going to explore the fascinating world of food, chemistry, and safety when it comes to animal products. From that juicy steak to your morning eggs and glass of milk. There's a lot of science happening behind the scenes to make sure what you eat is not only delicious but also safe. So, have you ever wondered why steak turns brown when you cook it, or how milk is treated to last longer on the shelf? It all comes down to chemistry. Let's start with meat. When you buy a fresh cut of beef, its vibrant red color comes from a protein called myoglobin. Myoglobin's job in the muscle is to store oxygen. When it's exposed to air, it binds with oxygen to form oxymyoglobin, which is that bright cherry red color we associate with freshness. Over time, or with a lack of oxygen, it can turn into metmyoglobin, which is brownish. This doesn't necessarily mean the meat is spoiled, but it's the first step in a series of chemical changes. Now, let's talk about cooking. That sizzle on the grill. That's the start of one of the most delicious chemical reactions known to foodies, the Maillard reaction. This isn't just simple browning, it's a complex reaction between amino acids, the building blocks of proteins, and reducing sugars. When you heat meat to temperatures above 300 degrees Fahrenheit, or about 150 Celsius, hundreds of different flavor and aroma compounds are created. This is what gives a seared steak, grilled chicken, or even roasted pork its incredible depth of flavor and appetizing brown crust. It's the magic that transforms a plain piece of meat into a culinary masterpiece. But flavor is only one part of the story. Safety is paramount. Cooking is our first line of defense against harmful bacteria like Salmonella or E. coli that can be present in raw meat. Heat denatures the proteins within these microorganisms, effectively neutralizing them. That's why using a meat thermometer is so important. It's not just about getting the perfect medium rare, it's about ensuring the internal temperature has reached a point high enough to eliminate any potential pathogens. For example, poultry should always be cooked to an internal temperature of 165 degrees Fahrenheit or 74 Celsius to be safe. Let's move from the grill to the dairy aisle. Milk is another staple animal product with its own unique chemistry. Raw milk is an emulsion of fat globules suspended in a water-based solution containing proteins, lactose milk sugar, and minerals. To make it safe for us to drink and to extend its shelf life, milk undergoes a process called pasteurization. This involves heating the milk to a specific temperature for a set period, for example, 72 degrees Celsius for 15 seconds, then cooling it rapidly. This process, named after the great scientist Louis Pasteur, is incredibly effective at eliminating harmful bacteria like Listeria and Brucella, without significantly affecting the milk's nutritional value or taste. But what about when milk goes bad? The sour taste and curdled texture are due to the action of bacteria that survived pasteurization or were introduced later. These bacteria feast on the lactose in the milk, converting it into lactic acid. As the acid builds up, it lowers the milk's pH. This change in acidity causes the main